Hello, today we're gonna do waves again. Because I have a waves test. The last one was an investigation. Okay, waves. Let's see. Okay, so the first question, let me find it. The first question says a marimba is a musical instrument with resonant pipes underneath each note. Each pipe is tuned for the fundamental frequency, the fourth harmonic and the 10th harmonic. Resonant pipes are open at both ends. Draw a standing wave of the fourth harmonic. Label each displacement note and antinote. So that's part A. Basically gave this. So we know that a fundamental in an open pipe like that, fourth harmonic just means there's four of these. So you can just draw like that's half. Okay, that's a bit big. We should do them one dotted. Okay. That's basically what it will look like. And this is a node. Let's just do node right here. Antinode, which are right here. Antinodes actually, okay. For part B, it says one of the longer pipes is 1.22 meters long. Calculate the frequency of the lowest note produced by the pipe when the air temperature is 25 degrees. From the formula sheet, we know that air velocity will just be velocity just be 346 meters per second and 25 degrees of a sound. The length is 1.22. We want to find the frequency because we know that V equals F lambda equals F because open pipe to LF over N. And that can lead to the equation that 346 equals 2 times 1.22 Fn. And because this has the lowest frequency, lowest note produced, so its lowest frequency, we don't know the harmonics. So honestly, we do know the harmonics because the higher the harmonics, the higher the frequency. So it should be the lowest harmonic, which is the fundamental frequency, which is 1. So n should be 1. But just in case, so it'll just equal, we will do 346 divided by 2 divided by 1.22, and that gave us 141.80 equals F over N. And because, okay, so for example, let's see if N is 10, we'll make the frequency higher, but that's not what we want because we want the lowest note. So N must be 1, and that makes it so that F equals 141.2 hertz because we're rounding it to 3 decimal places. And for part C, it says when constructing the instrument, a tuning fork is used to ensure the frequencies match a specific note. Initially, a note was played on the marimba and 6 beats per second were heard with a tuning fork that of 639 hertz. The pipe is then shortened until the beats were no longer heard. Calculate with reasoning the initial frequency of the note that was played. So final F equals to 639 beats equals to 6, and so F initial equals F final plus or minus beats, so that means equals 133 or 145 hertz. So for the initial frequency, and the pipe was shortened to produce a final, meaning that it have a longer wavelength but same velocity as original sound. Therefore, it have a short smaller, wait no, longer wavelength, so it should be a same velocity, wavelength frequency was smaller. So okay, it was shortened. So actually, it was shortened, so it should have a shorter wavelength, but the same velocity as original sound. Therefore, final have a longer, greater frequency, meaning initial must be smaller than 3639 hertz. Hertz. Okay. That's basically how you do this question. It's basic theory and thinking about it and understanding physics. For the next question, it's a big question for 6 marks. So it's a group of sound technicians are testing a new sound system at a concert using a signal generator. They're testing a specific frequency of 155 hertz. The speaker is situated at each end of the stage, which may it's gone. Situated at each end of a stage, which makes them 8 meters apart at their centers. The technicians standing at the back of the room, 8 meters from the stage, are socially distancing and are therefore 1.45 meters apart. Bruce is standing directly in front of the left speaker. Dimensions are in the diagram provided in millimeters. Assume that the speed of sound is 341 meters per second. Determine if Bruce and Fred experience a constructive or deconstructive interference. Okay. The diagram goes like this. Speaker. This length is 8 meters. It put it in 8,000. But I just feel like working with meters is way better than working with millimeters because it's pretty stupid. Bruce is here, so that is 8 meters, and Bruce, and then there's Fred, and then there's 2 other guys, David and Henry's, but they're basically not like cared about. 1.45. 1.45, 1.45. How to do this question is that we want to find the 2 sounds going through here and also here, and how different are their oscillations. So if this one's sine wave is like that, and when it reaches Bruce, it looks like that. And when this comes to Bruce, maybe it looks like like that. And that just means this was top, this is bottom, and they cancel out, and it never happens. And that means it deconstructs and doesn't construct. So yeah, that's how you do it. We know that sound, I think sound either can go like that, or for this speaker to actually reach, who is this? Henry, it should go like that. And this speaker should also go like that. And instead of doing this in waves, we can just calculate the straight distance, because these points should be the exact same as these points. So instead of caring about the points here, we just only have to care about the straight line and the waves on the lines. And same for this speaker. So let's do speaker 1, speaker 2, and 4. Let's do Bruce first. So Bruce, so basically, let's not do Bruce. Let's do V equals F lambda first. So 341 equals 155. Let's say 155 lambda, which means lambda equals 341 divided by 155, which equals 2.2 meters. That's the wavelength. So basically, the wavelength that is 2.2. And continue like that. It's another 2.2. That's the wavelength. So now we can use this information to Bruce. So for Bruce, 8 meters from speaker 1 straight. So there's no, so just 8 meters. So 8 meters, we want to find how many oscillations in 8 meters. So just 8 divided by 2.2, which equals to 8 divided by 2.2, which equals to 3.636. And a bunch of 3 6s. That is oscillations. So this should make it so that it looks like 1, 2. It should look like 1, 2, 3, and then it'll go like more than halfway. So look like, I think like that around. So like that. So that's 111, that's 0.6. And that's from speaker 1, speaker 1, speaker 2 should be, we'll have to find the straight distance from there to Bruce. So because that's 8 meters and 8 meters, that's just square root a squared and just times 2 because a squared. So it's just 2 times a squared. So that should equal to 11.3137 meters. We'll do the same thing, 11.3137 over 2.2, which is a wavelength. And we will find it to be 5.14259. How do you spell oscillations? Oscillations. Which means it goes like 1, 2, 3, 4, 5, and it only goes a little bit. So it should look like that. Yeah, 1, 2, 3, 4, 5, 0.1, 1. And if we look at where these are, this is slightly above, this is slightly below. That just means they clearly just cancel each other out. So Bruce will experience deconstructive, because one's positive, one's negative, you add them together, it becomes 0. Interference. Or what basically we can do is we can use, let's try that. Let's try it. Because we want to find the distance between them and then divide by the value, we can do 2 times a squared, 11.3137, subtract 8, divided by 2.2, and that is around 1.5. So that means the difference between these two is around like 1 and then that. So that just means they deconstruct anyways, because they're more close to a half less, and not close to a whole number. That's also how you can do it. But I like this way. This way is easier to understand. And we finished Bruce. Now Fred. Can you speaker 1? So basically, distance from speaker 1 is basically square root 8, because as we can see, if you want to find distance to Fred, it's a right angle triangle. So that's 8 and 1.45. So just 8 squared plus 1.45 squared equals to 8 squared plus 1.45 squared. That is around 8.13 meters. And we can find a 0.13 over 2.2, which equals to 3.695 oscillations. So that means it's like 1, 2, 3, and that much, a bit like that. It goes like that. 1, 1, 1, 0.6, and then speaker 2, it goes like, because I go from here to here, we know that is 8. So we know that is 8, but we don't know here 8, but here we know this is 1.45, so it's just 8 minus 1.45. So what we can do is we can do 8 squared plus 8 minus 1.45 squared. And what that will do is that will find us the distance. So it's root 8 squared plus 8 minus 1.45 squared, and that is 10.339 meters. And 10.339 meters divided by 2.2, which is 4.699 oscillations. That means it's like 1, 2, 3, 4, and then it goes like there again. That's 1, 2, 3, 4, and that's 0.6, 1, 1, 1, 1. And because look at these, they're going at, well, it doesn't go up again. So it goes around like that. Look at these. These are like basically the same. This one's just a bit longer, but they reach the same place. So if you add them together, they'll just construct each other. So because, for example, these are both negative, so maybe the -1, they become -2 instead of cancel each other out. So that means Fred will experience I can't spell anymore. Experience constructive interference. All right, that's basically how this question works. Maybe you can explain a bit more, like words wise, but the calculation is basically like this. Or you can use the other way, which you minus them first and then divide by 2.2, but this way you can explain as well. So that's that. So, oh well, bye bye.